So I've been an architect at Bol for over 16 years, designing all kinds of systems. And for those who don't know me, being an IT architect, I usually have quite unexpected ideas, make them reality, and while doing that, I scare people. This is one of those talks about a hobby. So let's start with a bit of history. Me and my green energy things. Well, it started out about 15 years ago when we got our new house. We moved in and it was an electricity-only house. No gas line, no externally provided hot water, none of that. We had a heat pump. And that means that there is a heat exchanger in the house, something like this. A central pit that pumps up the water from very deep, and that was used to heat the house. They told us it's proven technology. That's water vapor. And they told us it will be cheaper. Yeah. So a little over a year later, it turned out that we had quite a bit higher energy bill than we were told. So I started doing some measurements. I have to know where that energy is going. How much is that thing using? So I started with counting the blinking light on the electricity meter. That's not accurate. I got one of these to measure the actual values of the heat pump itself. So I put that in between. So I had two electricity meters. And using this, although it was very inaccurate, we found that that device by itself used as much electricity as a normal household. Our energy consumption was about 9,000 kilowatt hour per year altogether. A while later, we got a new meter which had a P1 cable. I could read the data and actually get it more accurately. That's awesome. And we got solar panels. Ooh, that inverter can be read over TCP/IP using a protocol called Modbus. Oh, wait a second, if I can do that, maybe I should recreate the measurement of electricity for the heat pump and do something smarter. So I got, that's an electricity meter, power supply, and a Raspberry Pi that sends out the data once a second. That's awesome. A couple of years later, after 14 years, the heat pump was up for replacement, getting a bit old. And we were told that the new ones were much more energy efficient. And the one we have now actually uses about half the electricity of the old one. So it went down to close to 2,000 a year. So that was really worth it. And over all of the years, I created the homegrown dashboard. You know, it's what you do. So I have an InfluxDB where I throw all the data in, and a Grafana dashboard. And I have electricity consumption all over the place. I have some graphs, and because I can subtract things, I can see, oh, this much is the house using, and this much is the heat pump using. And in addition to that, I have things like voltages, amperages, and all kinds of measurements that I can see in real time. But also, because I've been running it for many years now, I can actually look at what the energy consumption and production has been over all of those time. Now that's all nice and well, but hey, a P1 port, Modbus, how does that all work? And this is where the story goes downhill. This is where the technical journey goes really into the dark side of how these APIs work. I've ordered them from nice to not so nice, and unless you've been there, you cannot be ready. It's bad. Let's start with the nice one. The electricity meter has a P1 port, which adheres to the Dutch smart meter requirements. And it's a Dutch countrywide standard, so all modern electricity meters follow it, and it's a text format based on MBus. It's well documented. You can just download the specification. I even had some questions about the specification which were unclear. They promptly answered all of that. Awesome support. And you can just buy a ready-to-run cable, shove it into a Raspberry Pi or some other device, and you just get a record of data every second. If you have a slightly older meter, it will be every 10 seconds. And what does it look like? Well, it's a text format. So it starts with some specification about the type of device. It has a timestamp, and the W means it's wintertime. There's no explicit time zone specified, but because it's the Dutch smart meter requirements, we have to assume Europe Amsterdam. And it reintroduces the Y2K problem. Why? But anyway, that's how it works. And it contains information like the number of the device, about total values, about how much you have consumed and fed back. And it even has, for example, a power failure log. And this is essentially a list with one element, and there was a power failure at that timestamp. And then the S means summertime. And then if you go down that thing, you have current values like what's the current voltage, the amperage, the power consumption, all those kinds of things. And it closes off with a checksum to verify that there weren't any read errors. That turns out to be very useful, because it turns out that the clock in my electricity meter is bad. It's really off by several seconds. So if you want to put that data into a real-time graph using that timestamp, it will always be off. So what I'm doing is I read the data and then attach the timestamp of my local machine to it, which is NTP synchronized, and then shove it in InfluxDB. And I have periodically bad telegrams. So checking the CRC is actually quite important, because otherwise you get garbage. This was the nice one. Going one step down, Modbus. The other devices I have speak Modbus. And that is a 1970s binary protocol. You can do it over a serial cable, you can do it over TCP/IP, but it's a binary protocol. Funny thing is that the Wikipedia says not to be confused with MBus, which is what the smart meter uses. And then on top of this binary protocol, you have to have some software that does this. Open source library. Apache project, that's the one I use mostly. Well, what's the problem with Modbus? It's defined well enough, confusingly, or not at all, depending on where you look. So let's start with the basics. You have bits and registers, and depending on whether they are read-write or read-only, they give them a different name. And the company that came up with it, Modicon, had a notation, which is a number, and these are the numbers that they assign to it. So there you know, like, oh, this number is a discrete input number, this and this. First thing I go like, what happened to the 2 range? Nobody knows. And one thing that I've noticed is that this is really a protocol, a notation of a binary protocol with a base 10 mindset. You'll see some examples of that later on. So if you want to access those bits and registers, if you look elsewhere, you'll find a table like this. First thing, oh, they are called differently. Oh, somebody thinks they're analog. They're registers, they're bits. They're not analog. And these are the data addresses to query. They're all the same. And before I explain that, the first thing to notice is that they're off by 1. The numbers and the binary are off by 1. And because sometimes companies specify the one and sometimes the other, it is a mess. And it's also good to see that because it's actually a 16-bit number, you are not able to use about 85% of the address space using this notation. Now, how do you know which you have to do is that they have a function code. Okay, function code, right? So you have a 1 to read the coils, 2 to read the inputs, etc. And if you look closely, you will see that these have been swapped, 3 and the 4. That will not cause any confusion, trust me. And then if you have to write them, okay, so 2 out of the 4 are writable, so you have 5 and 6. They're writing a single one. Okay, so you also have, if you want to write a multiples, you have a different call to do. putting those all together, you get this enormous list of variants. And this is also where you see that the transition from single to multiple is a +10. So it's not a binary thing, it's really a decimal thing. And that's one of the examples where I go like, this is a really messed up thing. But we're still stuck with, we can only use 10,000 of these, of each. What if we want to go beyond that? Well, the integer notation is limited to 10,000. So somebody came up, well, yeah, you can do 6-digit. Okay, but then you have to go to seeing it as a string. Because if you don't, you know, you can get confusion. Because which one is it if it's an integer? You cannot discern it anymore. Luckily, there's also another notation that you see once in a while, and that's with an X in it. That makes it a lot better parsable. So in Modbus, if you want to transfer data, you need to know what you want to transfer. You figure out, you get the specification of the address. You have to try to parse that, avoid all the edge cases. Then figure out if you're writing into how many to get the right function code. And if you have that, then you have to do the off by one magic. And then you want to shove it into a library that actually does it. And you probably have to reverse half of that. Few more remarks about Modbus. Because most of these devices have very, very limited CPU power, they are slow. Having a request take half a second is not uncommon. Modbus is a binary protocol. It's a remote peek and poke. It doesn't tell you the meaning. And if you want to read, you can do at most 125. If you want to write, it's at most 123. And a lot of devices specify lower numbers. They say like 80 or something. And the big problem is that naming the documentations between the various vendors is inconsistent as hell. So let's examine the devices I have. And the first one is this electricity meter. I have the 3-phase one because the heat pump is a 3-phase device. And the specification is actually quite simple. All the parameters are read-only. All the parameters are 2 registers and have to be interpreted as a 32-bit floating point. You can only read 80 registers at a time, so 40 of them. And as you can see, the naming of the addresses is they have the off by 1 modicon notation, which they call the address, and they have the binary version of what is actually the wire address, which is what's actually in the protocol. This is actually quite doable. This was one of the first I implemented. That's easy. Now, my heat pump takes it up a notch because it introduces more things. First of all, the naming is different. What is called here the address is the wire address, not the off by 1 one. This is the real one. And the de facto address is the off by 1. So that becomes confusing. And then they say like, yeah, okay, these are the analog registers, the input registers that you have to read with function code 2. Analog, well, yeah, it's a 16-bit integer that you have to divide by 100 to get the value. So it's an integer in the data, but you have to interpret it with some math to figure out what the real value is. And they have more types in the set of analog registers. For example, this is an enum indicating what is currently being run, and a bit field with the bits of the things that are currently running, which can be multiple. So these are clearly not analog fields. And the third device I have is my solar inverter. And this is by the company SMA, and it has 2 sets of Modbus parameters you can read. The SMA specific ones and something called SunSpec. Now SunSpec is the interesting one because it's a standard across many devices. So instead of going into the SMA, I'm going into SunSpec. It's an industry kind of standard. Many solar devices support it. And it's created by an alliance of companies that have a business interest in this. And it covers solar panels and battery systems and all kinds of stuff like that. Key is that not all devices have the same functionality. My solar system does not have a battery capability. A battery system does not have solar capabilities. So what SunSpec really is a collection of what they call models. And each model encapsulates a specific sub-functionality a device can support. So each device has a custom list of models. And what I like about SunSpec is that they're really explicit. They take out a lot of the confusion about addresses and offsets. So they say everything has to be a holding register. There are specific addresses where it starts. They explicitly say it's the zero-based address. Cool thing to note is that this, because they are saying you can have it at 40,000 or 50,000, is that it completely makes the old mod icon notation impossible because you will go way beyond the 10,000. And they say it has to start with a certain header marker, which is the ASCII representation of SunSpec, SunS. So how does it look in reality? Is that if you have such a device, you try each of these three addresses, and then you find the start header, okay? And then what you get is an ID, a register with the ID of the model, a register with the number of registers that follow in the actual data, and then the actual data. And this is a repeat many times. It depends on the device how many, it depends on the device which models are present, and then at the end you have one with size 0, which closes the list. So you cannot have a fixed interpretation. You actually have to scan the device before you can know how to interpret it. And if you look at my device, you actually see this. So you have the registers. Then you have model 1, 42 hexadecimal bytes. You have them, and then the next one, and then that repeats until the last one, which is closing. Okay, but how do I interpret that? Well, they put the specification of those models on GitHub. JSON files, you can just download them. And there you can see model 11, which I had in the previous slide at the bottom, is something about wired Ethernet support. Okay? And then looking at that, you see it has things like interface status and link speed. And here it has link state, is it enabled or testing or stuff like that. And all kinds of variables that are relevant for specific that functionality. If you have a device without the capability of a physical Ethernet port, this model is simply not there. Now the schema of SunSpec is slightly more complex because it also has static values where they in the schema say this will never change. That's nice because in reading, because of the devices being so slow, you can optimize on that. But they also have repeating blocks. So you have a model which consists of a block and a certain other block which repeats multiple times, like in a list. And they now have in the more recently added models, they have even multiple repeating parts. So, you know, actually determining what the schema is becomes harder and harder. And then there is scaling factors. Now, scaling factors are really fun. If, for example, you have a variable somewhere, which is a current, amperage, they say it's an unsigned int 16, so single register, and it has a scaling factor. And this is actually the name of another property. So a bit later in the model, you'll find that property, which is an int, a signed int, which can be between -10 and 10, which has to be applied like this. So you take the register, then you interpret it as an integer, and then you multiply it by 10 to the power the value of that one. So the construct of that becomes pretty hard. And then I wanted to have, you know, this is, and the device is being slow, and I want to have local testing, and So I wanted to dump the data. You know, dump the data to my machine, have it as ASCII in the unit test so I can run it more quickly and test it and debug it all much easier. So I did that with the electricity meter. And it worked fine, you know. They're all nice registers and I could do that and work. But then I tried to do that with this SunSpec device. And I was having these weird effects, like really weird. So to show what happened, one of the fields in the specification is the name of the device, the type identifier. And my model, it has a disk string. Fine. Binary, it looks like this. So it's a couple of registers, and the ones that are not used are 0, because in Unicode, 0 is a meaningless byte. It doesn't exist in Unicode. So this is the representation. But when I was dumping that data, I was just dumping it in blocks. You know, fixed site block, just dump it. And what was happening is something weird. Because you can't dump it without knowing the schema. Because if I dump exactly these 16 registers, I get these values. Awesome. I have the data, that is correct. And I've actually tested this, if I only read the first 15, so I start at the right place, and instead of 16, I read 15 registers, I get an invalid address error. If, however, I start one register late, so I don't read the first one, but I start at the second one and then start reading it, I get a valid response. Not. Only once. So this is the kind of mess that Modbus actually is. So what did I do? Well, having done a lot in open source, I started doing some open source. So for the Dutch smart meter, that's easy. It's a push model. You listen and you get pushed the data every second in my case. You parse it, you read it, you process it, you shove it to where you want it, and it's fine. So I wrote a parser with some library code to handle that. Works beautifully. I use it at home. And recently I added an experimental thing where I can start it and have a GraphQL interface where I can have a subscription. So I can subscribe to the changes in GraphQL and get them pushed when they arrive. So this is all fine. Modbus, however, is a pull model. You actually have to fetch the data. You don't get it pushed, you have to pull it. In order to be able to pull it, you need a schema. It's slow, so you really want to optimize what you're pulling and how often and when. And the interpretation of the registers, as you've seen, is not trivial. Now, my first implementations, which are actually still running at home, were very device specific. Were not reusable, were bad code actually, but it works. So a while ago, about a year ago, I started trying to make this into more generic software. So the idea is that you have an application that needs some values. Then there is what I call a logical device, which has all the fields to the registers, a buffer, a cache of all the values that have been retrieved with a timestamp. So you can say, I want this value, and it's fine if it's 10 seconds old. So then it looks at the timestamps and decides what to refresh and what not. And that's the optimizing fetcher that tries to optimize that. It's all a bit shaky right now, but I'm getting there. And what I consider to be the most important part, a clean abstraction across all the Modbus address formats. A parser and a generator and a clean abstraction to handle all of the nasty effects cleanly. And behind that is the actual Modbus implementation, which I've kept open so I can swap it out easily. Now, my representation of all the green parts here is that I've created a custom language, actually created a parser, that supports the old Modicon formats, the parsable formats that are still off by one, and something that I prefer to use, which is the actual wire format without all the offsetting. I have created functions that parses the bits into numbers, into strings, into enums and bit sets, and a few special cases. And I've introduced a few functions to allow swapping bytes and doing endian changes and stuff like that, because some devices have that. And also, for the Dutch people, PEMDAS is similar to meneer Van Dalen wacht op antwoord. It's about ordering operations in mathematical expressions, and that is fully supported also. So what you then get is that, hey, I need that address is a 16-bit integer. It's a simple expression like this. Or I have from that register, I have 13 registers being a UTF-8 string, can be written like this. And the whole sunspec scale effector thing can be written like this. And sunspec specific, I have written something that downloads all of the models and then actually walks the chain and uses the downloaded JSONs to generate all of that on the fly. It's hard, but it kind of works now. And I'm working on, and this is still very fragile in my code base, something that allows you to have a schema as a file. So if I figure out the schema with all the expressions, somebody can share it. So I can write it for a device, and if you have the same device, you can reuse that. And also that allows new devices to be much easier added to the system, because somebody who has a device like that only has to create a YAML file like this. And it supports all the things that I've just shown, like the UTF-8 string. It supports the enums with the not implemented pattern and all the values that can be there. Same for the bit set. You know, it's an address with a not implemented and all the bits, what they mean. And also the scaling factor thing, that also works, because this is an example from Sunspec where we have a lot of voltage parameters that all share the same scaling factor parameter to work correctly. So what's the progress? Currently, I'm trying to convert it into Kotlin, because I want to learn Kotlin, and I think it's cool. I want to also be able to generate code. So if you have a schema that I generate code where you actually have hard-coded functions, that should make it easier while developing, so that you don't have to look up in an array or stuff like that, but you actually have much better developer support. But the Sunspec variant will be hard in that. When I'm confident enough it's actually working, I will open source it, but that's a not yet. And something that I really want, but I haven't figured out how to do that yet, is I want to be able to do a GraphQL subscription. But at the moment you do the subscribe, you specify the fields and then push down all of those into the actual loading mechanism, that only those fields are loaded that are in the requested subscription. Looking at all the libraries that I have seen so far, that seems a bit hard. So, summary, many of these APIs are bad, as in really, really hard to get right. And all I'm trying to do is trying to abstract them away so fewer people need to suffer. Thank you.
I think we have time for maybe one question. Are there any questions in the room? All right, let's see how that's gonna go. Okay, really sorry about that. Next time I'll just hand it to you.
Hello. So my question is, are there no better controllers that you can simply use instead of going through all this pain? So buy a new energy meter or something like that?
I have a solar inverter and I do not have a choice. This is it. I have a heat pump. This is it. The electricity meter, yeah, maybe. That's a small device that is cheapish that I could replace. But at least the solar inverter and the heat pump, no, those are in such a price range that these are the ways these systems have interfaces. And whether I like it or not, this is the way apparently this side of the world works. Unfortunately. Yeah.
Cool. Do we have any other questions? Throw it back. Okay, you're gonna try all the way there. Good luck.
Okay. Microphones are deadly.
Hello. Has the company Home Wizard already contacted you to see if you can work for them?
Well, actually, I have a water meter from Home Wizard at home. And the electricity meter that I have, actually Home Wizard has a variant of the exact same one that they have linked to their dashboarding solution.
Yeah.
So I suspect that they have worked with Eastern to make, a different interface on the same data. But that thing is the one with the Wi-Fi access is only available from Home Wizard.
Yeah.
I
Yeah,
have
so that's a
checked.
closed-
They only have that.
yeah.
It is really a closed system.
It's a closed system.
And I don't like closed systems.
There are a lot of, there's a big community of tinkerers, let's call them,
Mhm.
that are doing this kind of stuff. So please release this to tweakers.net or something, because a lot of people want this. So yeah.
I think a lot of people want this, but at this point in time, the code is not good enough to show to people because there are certain things I want to figure out first before I publish it. One of the things that I hope, which is really a vain thing to say, is that if I can get this expression language and the YAML format in a clean way, it can be used, from my perspective, as a standard. And people can create different implementations of the same thing and have a Python library or a Go library or a Rust library reading the same specification format. One of the big problems that I have with the vendors is that they publish their Modbus specification in a PDF with tables. And then they have the PDF with the tables so crappily formatted that if you do a copy and paste, you get a mess if you paste it, because all the columns and rows are messed up. And so this format, that's also why I'm waiting until I'm sure it is good. If this format becomes usable for others, then others can say, oh, I'm gonna re-implement this in a different language. And that would really make it a lot better for everybody.
Thanks.
Cool.
Can I ask 2 questions?
Sure.
First question is, do you suppose that it was like entry-level CS students who wrote this protocol and these specifications? I'm curious if you've done any digging to see like where these originally came from and why they're so poorly designed.
So my impression, and I have not done the digging, my impression is that it was written by people, by electrical engineers in the 70s, by people actually creating these devices. And then the computers were upcoming, and at that point in time, nobody had experience. Everybody was figuring it out as they go. Because one of the things is that in Modbus, I have yet to find, there is no security at all. Raymond is going to love me for this, but it's true. There's no security at all in there. And that is also where you go like, okay, yeah, but that was invented like a decade later. And that was realized much later. And all of the APIs we're now using, REST APIs, and now progressing to GraphQL, it's all, stepping up. However, this class of devices, these technologies, they have been stuck in the old ways. And that is also why I want with this library to at least attempt to expose it as a GraphQL, and then making it possible to expose these devices that physically are still in the old way and expose them in the new way and making it much better accessible to all the new tool stacks.
And maybe my second question.
And the last one, because everyone wants to eat.
Yes. In regards to your ability to test this protocol, you're limited by the devices that you have in your house.
Correct.
What is your approach as you think about making this more generic and abstracted? How do you handle that problem with different manufacturers and different devices that you don't have access to?
Yeah, that's a good one.
Yeah.
Yeah. Now, one of the things is that I've actually created for the Sunspec a library that is a precursor to all of this, that is on GitHub, where you can find it. And I recently got somebody who had a really large solar installation that was using it. And he said, yeah, I have a problem with this and this and this. And he sent me a dump of all his registers. And that's you know, the alternate data set that I'm using to make all of this work. And you know, having access to physical devices is also for the Sunspec part. Some of these parts are really tricky, and I do not have real data to verify how it actually works. It's a problem.
All right. Thank you, Niels. If you have any more questions, I'm sure he's happy to answer them during the lunch break and during the coffee break, so you can find him. Before you all run to lunch, there's also a community fair you can visit during the break, and there's also some breathe and stretch sessions if you want to relax. And now you can go eat. Enjoy.